Hello friends, welcome to engineering tutorial. So we'll continue our discussion on thermodynamics. Previously we discussed about the basic mechanism of thermal conduction and about the variable and steady state, the two phases in thermal conduction and temperature gradient. So in this video we are going to establish a mathematical relationship for heat flow or thermal conduction in the form of a mathematical formula and discuss the various factors which come into play when heat flow from one point to another is taken into consideration. So just a quick recap. So thermal conduction, basically it is the process in which heat is transmitted from one part which is at a higher temperature to another point which is at a lower temperature through continuous molecular collisions. Now we all know that every substance, it consists of molecules, and the molecules possess three types of motions, because of which it has its own kinetic energy in each category, that is translational, vibrational and rotational. And when any one point on the object is heated, it undergoes an increase in the average kinetic energy and high amplitude oscillations or vibrations. And as a result, when these high energy molecules, they collide with the neighboring adjacent molecules, they transfer their energy to them, and they start a whole chain reaction in which they also collide with their neighboring adjacent molecules, transferring their energy, and in the process the whole object gets heated, through continuous molecular collisions, high energy, high vibration or oscillatory motion of the molecules. So if we want to establish a mathematical relationship for thermal conduction, so let us take a situation. Let's say we have a metallic block in the shape of a cube. We are assuming it's in the shape of a cube. There are two faces. This face, which is at a higher temperature, we are calling it hot face, which is at a temperature T1. And another face which is at a distance x away from this hot face, which we call cold phase. Cold phase means it is at a lower temperature than T1, that is T1 is greater than T2. Now we know that heat flow basically happens between 2 points which are at a temperature difference, high temperature to low temperature. So naturally heat will flow from T1 to T2, from this side to this side, which is direction, shown by the arrowhead. So this is the heat flow. Now here the area of each face is A, and the separation distance between the two faces is x. Now experimentally we have, it has been found that the amount of heat flow Q is dependent on these factors, whether direct or inverse relationship. So the amount of heat flow Q that flows from the hot to the cold phase in the steady state, not the variable state, steady state, when different points they acquire a steady temperature beyond which the temperature cannot increase. So for more of that, you please refer to the previous video on steady state, variable state and temperature gradient. So it has been found that the heat flow during the steady state, it is directly proportional to the cross-sectional area. It is directly proportional to the temperature difference between the hot side and the cold side, that is T1 minus T2. It is directly proportional to the time duration for which the heat flow takes place. We call it, let's say, T, small t. And it is inversely proportional to the separation distance, that is the thickness of the block or the separation distance x. So here we combine all of these, okay, where Q is directly proportional to the cross-sectional area, directly proportional to the temperature difference between the hot and cold phase T1 minus T2, time duration for which the heat flows, that is small t, and inversely proportional to the separation distance or thickness of the block. So here a proportionality constant capital K comes into play. Okay, this is basically, it represents the nature of the material of the block, whatever the material the block is made up of. So that represents the proportionality constant capital K. So the heat flow relationship is expressed by this Ka T1 minus T2 into T by X. Okay, here please pay attention to this part, T1 minus T2 by X. T1 minus T2, it represents the temperature difference, del T, or in differential form we can write it as dt. X can be written as any displacement or gap, so we can write it as delta x or dx, because let's say we pick any 2 points in space, okay, in a 3-dimensional space or in any direction, and we want to know the gap between them. So this will be the thing, delta x, the gap between these 2 points. Let's say from the origin this is 1 point and this is 1 point. Let's say this is x2 and this is x1. So this gap between them, it will be equal to x2 minus x1, or we can say final position minus initial position, in whichever way we want to represent it. So we can write x as dx. So this relationship of heat flow, it takes this form. Q is equal to Ka dt by dx into T, or Ka delta T by del x into T. Now if you remember, dt by dx is nothing but temperature gradient, which we have discussed in the previous video. Rate of change of temperature with respect to distance. So dt by dx is the temperature gradient. Here there is another interesting thing. Here, if we consider the direction of heat flow from the hot phase to the cold phase, as we move away from the hot phase towards the cold phase, temperature is decreasing, because heat flow always takes place from a higher temperature to a lower temperature, hotter side to comparatively cooler side. So that's why here this dt by dx, it will become negative, because temperature is decreasing in the direction of heat flow. So if we have to write it in an appropriate manner, taking into account the direction of heat flow and the temperature gradient relationship, it will be like this: Q is equal to minus Ka dt by dx into T. Okay, so the negative sign, it indicates that the temperature gradient, that is temperature is decreasing in the direction of heat flow. That's why temperature gradient is negative. Okay, so this is the proper relationship. But if you are only concerned with the magnitude of heat flow, then this is the relationship, Ka dt by dx. Only the negative sign here indicates that as we move away from the hot phase to the cold phase, temperature is decreasing, or temperature gradient is negative. That is the meaning of this negative sign. So these are the factors which affect thermal conduction. So basically it means the heat flow is directly proportional to the cross-sectional area. So the more the area, the more will be the heat flow, the magnitude of heat flow. The more the temperature difference, because it is directly proportional to the temperature difference, so the more the temperature difference, the more will be the heat flow. And then the more the time duration for which heat flow takes place, the more magnitude of heat flow it will be there. And it is inversely proportional to the separation gap. So it means if these two faces are closer to each other, the heat flow will be more, and if it is far away from each other, the heat flow, it will be less. The magnitude of heat flow, it will be less, because it is inversely proportional to the separation gap or the thickness. Okay, so this is the thing. Okay, so now is the coefficient of thermal conductivity, this K, this constant, proportionality constant K. Now suppose here we consider a block, okay, where the cross-sectional area is 1 meter square, the temperature difference is 1 Kelvin, the separation distance is 1 meter, and the heat flow it takes for 1 second. We consider a 1 second time duration. In that case, everything else is one unity, so it will simply be Q is equal to K. So that gives us an important definition of the coefficient of thermal conductivity. So it can be defined as the quantity of heat that flows per unit time, that is T is equal to 1 second, through a unit cube. It means area is equal to 1 meter square, the area of the face, and the opposite faces are kept at a temperature difference of 1 degree. T1 minus T2 is 1 Kelvin, and unit cube means area of the face is 1 meter square, and the distance between the two faces, the hot face and the cold face, that is equal to 1 meter. X is equal to 1 meter. So Q is equal to K. Okay, so the coefficient of thermal conductivity can be expressed as this. We know that Q is equal to K T1 minus T2 into T by X. So we can write K as this, taking all these factors towards the LHS side. We can write K from here. If we take Qx and A into T1 minus T2 into T to the denominator, X goes to the numerator, A into T1 minus T2 into T goes to the denominator. On this Q side, we are left with K is equal to this much. Okay, this is the relationship. And suppose we want to write it in temperature gradient form, then we know Q is equal to Ka dt by dx into T. So K is equal to Q by A into dt by dx into T. Okay, this Q by A into dt by dx into T. Okay, so this is the relationship. And this is the expression for coefficient of thermal conductivity, and this is the definition. So the unit of coefficient of thermal conductivity, that is joule per second per meter per Kelvin, because heat flow has the unit of joules, and these all represent here, as we have seen. Area is meter square, separation distance is in meters, time duration is in seconds, temperature difference is in Kelvin, and this is here the unit of coefficient of thermal conductivity in SI, joule per second per meter per. Okay, so here we have discussed a very important concept which gives us all the factors which affect thermal conduction or heat flow, and also gives us a mathematical relationship of heat flow. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.